Okay. So thanks, Jianfeng, for the introduction, and also thank all the organizers. So actually, my talk is about actually some applications, and especially statistical applications of tensor methods. Okay, so this is based on a joint work with my colleagues and my student. Okay. So first of all, let me briefly explain the motivation. Okay, and actually, our motivation is to study some community structures in some complex networks. So first of all, let me briefly explain what is the meaning of community structures in networks. And here, this is a real data example. It is about the American college football team data set. And here you can see it is a network, or mathematically, it is just a graph. And there are vertices, and actually every vertex just represent one college football team. For instance, you can see the UCLA team here, and also maybe Stanford here. Okay, and there's an edge between two vertices. Okay, if these two teams played a game in the year 2001. Okay, and this graph is obtained by is obtained from this science paper. Okay, and in this paper, or in this network, and actually you can see there are for this vertices, right? You can see there are colors, and actually the colors doesn't mean that. Okay, some group structure for this vertices, and especially for this vertices, they are in the same color, means okay, they come from the same conference. And of course, for this kind of structure, we can consider, right? We can consider, okay, what is the difference here, right, in the networks? And usually it is observed that okay, if two teams belong to the same group structure, or to the same group, then it is more likely that they will play a game, or in other words, there's more likely to be an edge between two vertices if they belong to the same group. And however, I have to mention that okay, in many real applications, what we observe are only these vertices and these edges, and we have no idea okay, which vertices belong to the same group or same community. And our goal is to find out okay, to cluster these vertices into different communities. Okay? So this is a typical example of a community structure in networks. But nowadays, there are more and more complex networks. And one specific example is so-called the multi-layer networks. It means that okay, now we'll have many layers of networks. And here is a very interesting example about the international trade flow. It is also some real data from the United Nations platform. Okay, so here every vertex is just a country. Okay, and every layer is corresponding to the trading flows of one commodity, and there are 100 different types of commodities. In other words, in this data set, we have 100 layers of networks, and every network is about the trading flows between 50 countries. And here I present to you two layers of these networks. So one layer is about the trading flows of mineral fuels, and another layer is about the trading flows of cotton. And you can see here there are some countries, right? And the colors of these countries just mean okay, they come from some continent. For example, USA, Mexico, they come from America, and for Malaysia, Japan, and Egypt, they come from Asia. Okay, so this is one example of multi-layer network, and another example is about this malaria parasite gene networks. So here, every vertex means one genetic sequence. Okay, and in other words, here every node is just about a genetic sequence, and there's an edge between the two vertices if somewhat they have similar functions. Okay, and here in this data set we have observed 9 high variable regions, and in each of this region we can observe 1 layer of network. In other words, in total we have 9 layers of networks, but here I only present to you 6 layers. Okay, and this data set is very interesting because you can see actually for some layers the network is even not connected. Okay, so of course we are not among the first to study the community structures, and actually there already exists many literatures on this topic. But however, for all these previous works, they assume all layers have the same community structures. In other words, you can imagine, right? If you assume every layer comes from the same community structure, then a very simple idea is to add up all these layers. But in this case, there's no meaning to apply some tensor methods, right? And also, if you observe this kind of networks, it is highly unlikely that, as you can see, for the 2 layers, it is highly unlikely to assume they come from the same community structures. Okay, so our motivation is that we want to study the community structures on multi-layer networks, and the community structures can be different across layers. Okay, so here is an example of also a real data set, and it is about the food trading networks. And actually we observe that, okay, if we look at the trading flows of unprocessed food and the trading flows of processed food, then the heat map of these trading flows, the patterns can be quite different. And that is one motivation why we want to deal with different community assignments or structures on different layers. Okay, but of course later I will explain more details for these examples. Okay. Okay, so now we have so now let me briefly explain, right? Well, what is the statistical model we're going to study, okay, to treat this multi-layer networks. And of course, in statistics or network analysis, there's one very famous model to study the community structures on 1-layer network, and it is called the stochastic block model. So basically, in this model, we observe 1 layer of network. So it is a graph, and suppose there are n vertices. Then, and we'll assume that for this n vertices, it can be divided into k disjoint communities. I mean, so basically, and the vertices in the same communities just mean, okay, they maybe share some similar features or characteristics. Okay, and we usually denote a binary matrix Z, okay, as the membership matrix. In other words, for this matrix Z, every row is corresponding to 1 vertex, okay, and then for every row, it has only 1 entry is non-zero. And here is an example for this membership matrix. For this example, you can see it has 6 rows and 3 columns. In other words, in this SBM model, there are 6 vertices and there are 3 different communities. And if you look at the first row and the third row, you can see they have only 1 entry equals 1. And it means that the first vertex and the third vertex, they belong to 1 community. And similarly, if you look at the second row and the last row, also they're the same. In other words, the second vertex and the last vertex, they belong to the same community. Okay. And also for this SBM, is also called probability matrix. It characterizes what is the probability of generating a vertex or an edge between the 2 vertices, okay, based on the community memberships of them. So for instance, if you look at this example, you can see for this entry, it equals 0.3. In other words, if we have 2 vertices, 1 vertex comes from the first community and another vertex comes from the second community, then the probability of connecting these 2 vertices by an edge is given by 0.3. Okay, it is the probability of generating this edge. In other words, in this SBM model, right, for all the vertices in the same community, they are considered stochastically equivalent. Okay, and this is the so-called SBM model. Okay, but now suppose we have many layers, right? Now how can we model the different structures, right? Different community structures on different layers. Of course, our very natural ideal is given like this. Suppose we have maybe, for example, maybe 6 different layers. Now we can maybe suppose that these 3 layers, they come from one SBN, and the other 3 layers come from another SBN. Okay, so based on this idea, we propose the so-called the mixture multi-layer SBN model. So, but please bear with me. There are some, somewhat complicated notations. Okay, so suppose we observe A layers of networks. Okay, so every layer is a graph, and we'll assume that in total there are n different latent SBN models, and of course every layer is sampled from one of this SBN. So in this case, in other words, every layer has a latent label. This label just means which class of SBN this layer is sampled from. In other words, the label can be any integer from 1 to n. Okay, and then of course we can denote some notation for this community, for its communities in each of this SBN. Okay, and then we observe the adjacent matrices for each of these layers. Okay, and in other words, we observe AL adjacent matrices. Okay, like this. Now you can see, right? It is very natural to treat it by tensor method. Okay. Okay, so this is overall the model for this work. Okay, and very interesting, if we define this kind of mixture multi-layer networks, and then we can define some new concept. One is about local communities. The meaning of local communities is very easy. It means the community structure on each individual layers. Okay, and also it's also called global communities. The meaning of global communities is that, okay, if 2 vertices I1 and IJ and I2, if they belong to the same local community on every layer, then we say that they belong to the same global community. Okay, and here is our simple toy example of this local membership, a local community, and a global community. In other words, in this example, suppose we observe 3 layers, right? And for the first layer and the third layer, you can see the community structure is the same. So in this case, we view them, right, as the local communities. And however, for the second layer, you can see actually the layer, the community assignment is different from the other 2 layers. Okay. Now you can see in this kind of example, we have actually several different tasks. The first one is that if we observe this kind of network, or this kind of many layers of networks, then first of all, how do we identify which layers belong to the same class? Now, of course, in this case, we know the first layer and the third layer belong to the one class, and the second layer belongs to another class. Okay, so in other words, we can first try to identify the network classes. Okay, and also if we put the community assignments all together, then you can see actually there are 4 different global communities. In other words, for the vertices in this group, you can see they belong to the same community on every layer. Okay, in this case, you can see we can define the global communities. Okay, and now let me briefly explain it overall what we want to do, or what kind of goals we want to achieve. So if we observe AL layers of networks sampled from this mixture multi-layer SBM model, then we have 3 tasks. The first task is to recover the global memberships of vertices. And the second task is to recover the data labels of network layers. In other words, we want to identify which layers may be sampled from the same class of SBM or the same class of models. And after that, we can also try to recover the local memberships of vertices. Okay, so this is our goal. Now let me explain how we treat it by tensor method. Of course, it's very easy to see that we can define the so-called adjacent tensor. Okay, in this case, it is a tensor of order 3, and the size is m by l because we have l layers. Okay, and of course, we also have to introduce some simple tensor operations, but I believe for all the participants in this workshop, it should be clear about this multilinear product of tensors and vectors. So I will skip them. Okay, now very interesting. Okay, if we look at this adjacent tensor, okay, and we consider the expectation, and actually it is very easy to see that the expected tensor admits a low rank decomposition. In other words, the expected tensor is a low rank tensor. Okay, and here we can define this global membership matrix. Okay, and here this W is also a 0-1 matrix. It can provide the information about the layer labels. Okay, for each of the layers. Okay, so this is where we start. Okay, for our later methods. Okay, to deal with the multi-layer networks. And of course, if we write the decomposition like this, actually, this decomposition is actually not easy to deal with because this matrix can be rank deficient. Okay, so a better way is to introduce a so-called the Tucker decomposition for this expected tensor. In this way, we can write it as a Tucker decomposition with a small core tensor and singular vectors. And for this singular vectors is very interesting because if you look at the singular vectors in the first and the second dimension, so we write it as a U bar. And actually, based on this singular vectors, we can recover the global community structures. And also for the singular vectors in the third dimension, it provides the information about the layer labels. In other words, our goals can be achieved if we can recover the singular vectors U bar and W bar, okay, of this expected tensor. But of course, the expected tensor is not available. What is available is the data, which is the adjacent tensor, right? But however, in general, right, it is of 4 rank. Okay, in other words, now we can write the data we have right into 2 parts. One is the signal part, and the signal part has a low rank decomposition or has a low rank structure, and the singular vectors can provide us the information we want. And also the second part is a noise part. Then the idea is very simple. To estimate the singular vectors of this signal part, we can try to obtain a low rank approximation of this adjacent tensor A, right? And then a very natural formulation for this problem is to solve this low rank approximation. In other words, we try to minimize this approximation error by choosing a small core tensor and the singular vectors U and W. Okay, so this is the first step. Then after this step, we can try to use the estimated singular vectors to do cluster. So the whole procedure for our method is given by this diagram. So first of all, we observe many layers of networks, right? Then from these networks, we can construct an adjacent tensor. Then for this adjacent tensor, we apply some regularized tensor decomposition and obtain the estimated singular vectors. Okay, and our method is called the twist. Okay, and based on this estimated singular vectors, we can do clustering, and we'll obtain the global memberships of vertices, and also the network labels, and then we put some layers together. But if these layers has the same labels, okay, then based on that, we do another step of clustering and obtain the local memberships. Okay, so there's a whole procedure. The idea of this procedure is very simple, but however, there's one very important step in our method. It's called the regularization. So now let me briefly explain to you the intuition for this regularization. So remember, right? What we want is a low rank approximation for this adjacent tensor, and of course, it is very easy to see that some this formulation can be somewhat equivalently written or rewritten in the following form. That means now we can throw away this core tensor and try to maximize, right, this term by choosing some singular vectors u and w. And to solve this problem, of course, it is highly non-convex, right? But however, we know that it can at least be solved locally. And was suppose we have some warm initialization, right? Then we can apply maybe some fast algorithm like the power iterations. Okay, but however, there exists additional structure information we can use. That is, in network models, usually the row-wise norms of these singular vectors are often small. In other words, for these singular vectors, they are often incoherent. Then, to take advantage of this additional structure information, a more natural formulation is the following problem. That is, again, we try to maximize, right, this objective function. But however, for these singular vectors, the row-wise norms should be bounded by some small number. Okay, so now, right, this is the real problem we want to solve. And then, of course, we can apply the power iteration algorithm. But however, to enforce this condition, we can apply an additional step, which is called regularization. In other words, in every iteration after we obtained an estimate of the singular vectors you had, we apply some truncation procedure. Okay, and by this procedure, we can guarantee that, okay, this estimated singular vectors are incoherent. Okay, so this is the intuition for regularization, and also we have from the theoretical point of view, we have another reason, okay, to introduce this regularization. Essentially, right, if we think about it, how do we analyze the accuracy of this power iteration? And you can see actually a very important step, okay, is to prove a sharp upper bound for this term. So here, this is the noise part, and we multiply it by the estimated singular vectors, right? And actually, if we do not impose any incoherence condition, in other words, this u hat and w hat can be coherent. Then in this case, for this term, in the worst case, it can be roughly the same order as the optimal norm of this noise tensor. And it is easy to see with high probability, this term is at least of the order 1. Okay? It is actually very large, and it will not be appropriate for us to use it to deal with extremely sparse networks. Okay, and actually, if you apply the incoherence condition in this case, in other words, u hat and w hat are incoherent, then we can prove much sharper bound. Okay, so this is the motivation. And of course, our next part is about the theory. So, but however, I don't think I have enough time to introduce the theory for this part. But essentially, right, we want to show you that, okay, if we introduce this tensor incoherent norm, okay, and we can if we prove a very sharp tensor incoherent norm, then our method can deal with very, very sparse networks. In other words, even if some layers are disconnected graphs, our method still works. Okay, so but however, I think time is not enough, so I will skip the theory part. Now let me briefly give you some, show you some results on this real data examples. The real data example is about the food trading networks. Just as I have already explained, right? In this data set, we have like 19 countries. So every country is regarded as one vertex, and the trading flows between these 19 countries, right, are obtained for 30 different food products. In other words, we have 30 layers of networks, and for every network, right, it is about the trading flows between 19 countries. And then we apply our method on this data set, and actually, after obtaining this estimated singular vectors, we apply the clustering for singular vectors, and actually we can cluster this many layers, okay, roughly in two classes. One class is here, and you can see, very interesting, in this cluster, you can see the food products are mostly the unprocessed food. For example, like the coffee green and the tobacco unmanufactured. And for the second cluster, you can see most of the food product are the processed food. In other words, the trading patterns for these two types of food can be different, and it can be detected by this tensor-based method. And of course, if we apply matrix-based method, it is impossible to. It may be possible, okay, but the result is not as good as the tensor methods. Okay, then we look at this the community structures for these two types two classes of networks. So for this for the layers of unprocessed food, you can see here this is the heat map of the trading patterns or the trading flows between countries. So here every row and every column is corresponding to some country. And for this unprocessed food, you can see actually the trading patterns is dominated by global tradings. But however, for processed food, you can see actually the regional trading dominates. For instance, if you look at this block, right? For this block, they are mostly about the countries from America. And also for this block, you can see they are corresponding to countries in Asia. And here for this block, they're corresponding to the countries in Europe. Okay, so this is the community structures in this example, and also very interesting if we do the node embedding for this vertices, and for this the second clustering of the second class of layers, you can see actually will obtain the node embedding as follows, and it is very close to our world map. So here are the Asian countries, and here are the European countries, and here are the American countries. And also I have another real data example, but I think time is up. Okay, so I will stop here. Okay, so thank you.